We've looked at how to do arithmetic for natural numbers, like 16-bit numbers that are all non-negative. Okay, but now I want to try to shift our attention to talk about all-day integers, right? How to do addition on all-day integers, how to do subtraction, those kinds of things. It turns out that the secret to all this is modular arithmetic, right? And modular arithmetic is, I might look, for example, at 23 modulo 5, and that's equal to 3. And what we're saying is that 3 is the remainder of 23 when it's divided by 5. Okay, so this operation, the modulo operation, is going to be the key to do subtraction, is the key to do negative integers in binary representation. To do modulo, then we have to talk about quotients and remainders, right? I mean, that's the whole point. The modulo is the remainder. So we want to bring up the quotient remainder theorem. Okay, this is something you already know, right? I mean, this is something that you learned, I don't know, probably second grade, third grade, something like that. And here's what we have. We have two numbers. So let's say that A is equal to 23 and B is equal to 5. Okay, we just need two numbers. Okay, and now we're going to think about A divided by B. Okay, and what we're going to do is we're going to actually write it like this. We're going to say that A is equal to some number times B, which is 5, okay, plus some other number, okay? We call this Q the quotient and this R the remainder. In this particular case, what we have is that it's 4 times 5 plus 3. Okay, so that's the first thing that the quotient remainder theorem tells us. We can always do this, right? Now, you might look at that and go, wait a minute, of course we can always do this, because A, which is, 23, is just simply 0 times 5 plus 23, right? So what's the big deal? Okay, well, the big deal is that we can always write A is equal to Q times B plus R, where this is an integer, okay? And this is an integer, but in a specific range. It has to be between 0 and b. Okay, and notice that this here is a less than. It's not a less than or equal to. Okay, so now you can't do 0 times b plus 23. You have to do 4 times 5 plus 3. Okay, now so this is the first thing that the quotient remainder tells us. The second thing that it tells us is that the values of q and r are unique. Okay, that's really powerful. Okay, because that's what justifies us talking about the quotient and the remainder. Okay, we've actually used the quotient remainder theorem quite a bit in the past. Okay, we just used it intuitively, like we've laid it out here, and I think it's certainly a theorem that you can believe is true. Okay, now let's talk about how we might state this theorem using mathematical notation. Okay, so what we have is that A and B are integers. Okay, B is greater than or equal to 0. Okay, so A belongs to Z and B belongs to Z plus. Okay, the reason we're doing Z plus is because we don't want to divide by 0. Okay, and when you look at negative numbers, then A divided by minus B, let's just think of that as minus A divided by B. So it doesn't contribute anything, right? So this is really all we need. B can be greater than 0. Okay. Well, once we have that, then I can find integers Q and R that have these two properties, right? So A is equal to Q times B plus R, right? And R is in this restricted range. Okay. And then of course that choice is unique. Okay. So that's the theorem, right? This is just notation. Q is the quotient, and I want to emphasize the word the because there's only one. And R is the remainder, again, emphasizing the word the because there's only one. Okay, so surely this is something that we all believe. You definitely need to know this theorem because we're going to be using it a lot when we're talking about modular arithmetic. You're going to see that this is the foundation for everything. But next up, I want to show you how to prove this theorem.